Hi, everyone. Thank you for attending this presentation. My name is Pablo Zinemanas. I am a PhD student at the Music Technology Group in the Universitat Pompeu Fabra. Today I'm presenting the work entitled Toward Interpretable Polyphonic Sound Event Detection with Attention Maps based on local prototypes. This is a collaborative work of researchers from the Music Technology Group and Universidad de la República. We are using sound recognition technologies for several applications that have a strong impact on human lives. For instance, self-driving cars, surveillance, machine fault monitoring, and even in healthcare applications. However, most of the systems used for these applications are black boxes. And the black box nature of these models may produce unintended effects, such as reinforcing inequality and bias and being vulnerable to adversarial attacks. Besides, the black boxes are hard to debug and troubleshoot. Therefore, there is a recent surge of research on machine learning models that provide explanation of the decisions, a field known as interpretable machine learning. This is especially important when high-stakes decisions are involved, like the applications we mentioned before. However, there is still a lack of research in this field in the audio domain. Most existing works on interpretable machine learning follow a post-hoc approach. They try to explain the input-output behavior of the black box model. For example, train a linear proxy model that imitates the behavior of the original model but is easier to interpret. However, since the proxy model is typically a local linear approximation of a nonlinear model, it can fall short of providing a reliable explanation. Rather than producing explanation of black box models, some research seeks to develop inherently interpretable neural networks that provide faithful explanation to what the model actually computes. By adding specific components, one can strive for rendering some form of interpretability while being as accurate as a black box model. In this sense, we have proposed the model called Audio Prototype Network, APNet. It has two main components, an autoencoder and a classifier. The role of the encoder is to represent the input in a latent space of user features. The decoder function is used to map the data from the latent space back to the input representation. The prediction of the classifier is based on a frequency-independent similarity between the encoded input and a set of prototypes. The weighted sum layer controls the contribution of each frequency bin to the similarity measure. Finally, this similarity measure is fully connected to the output to produce the prediction. Now, note that the prototypes can be converted from the latent space to the input representation by applying the decoder function. So we can see the reconstructed prototypes and listen to them. The audio prototype network showed compelling results when applied to speech, music, and environmental audio for problems with a single class label per audio clip. For instance, in this example, we have three prototypes. So when the model tries to classify a new instance, it calculates the distance from the input to each prototype and make a decision based on that. However, in a polyphonic setting, like the sound event detection problem, an input instance corresponding to several classes should be simultaneously close to prototypes of those classes in the latent space. Unfortunately, learning such latent space proved challenging in practice, thus motivating the alternative approach that we are presenting. The model proposed in this work is devised to overcome this limitation. It is capable of detecting simultaneous sound events. It uses the same autoencoder from APNet, and we use another encoder, S, to extract M attention maps in the latent space. Each attention map is related to one prototype, and note that each prototype represents one point in the time frequency plane in the latent space. Therefore, in the input space, these prototypes represent a patch of shape equal to the receptive field of the encoder network. We convolve the attention maps with the prototypes in order to reconstruct the latent representation. The attention maps represent the specific weight of each local prototype in each time frequency point in order to have a good reconstruction of the latent space. Using the decoder from the top branch, we can project this reconstruct tensor into the input space. In this way, we can visualize the reconstruction of the latent space in the input space to inspect it. Finally, the bottom branch deals with the detection task, which is solely based on the attention maps. First, we average the time dimension of these attention maps. Then, a dense layer connects the mean attention maps to the classification output. These figures show the performance comparison of the proposed models and two black box baselines and their number of parameters. Note that the performance of the proposed model is comparable to that of the baselines, but with fewer parameters. Besides, for each data instance, it's possible to extract the corresponding attention maps to provide an explanation on how the model makes its predictions. Note that the model can detect simultaneous sound events whose energy is concentrated in different frequency bands. Since the attention maps are designed to reconstruct the latent space and are the only information used for classification, this represents the inherent explanation of how the network makes its predictions. To conclude, let's summarize the key points of our proposed model. In this work, we proposed a novel interpretable deep neural network for polyphonic sound event detection. The proposed model learns attention maps used for positioning the local prototypes and reconstructing the latent space properly. Then the detection is solely based on the attention maps. Thus, the explanation of the network are in the form of local prototypes and attention maps. The proposed model achieves good results in urban sound event detection for the URBAN-SED dataset, which are comparable to that from two black box baselines, but with fewer parameters, while at the same time offering interpretability. Thank you very much. And if you have any questions, please let me know.